Morning students. In the last class we discussed about the chemical, some reactions of alkanes and haloarenes. Today we continue with the same. Okay. So I explained up to which reaction yesterday? Which one? Redundant oxidation. Okay. So further three reactions are there in the main is so reaction with AgCl and KCl is also important. Means what the product we are going to expect. Before I told you, with the aqueous KOH, we will get alcohol. With the alcoholic KOH, we will get alkene. Different products, right? So the before equations I explained. If we use aqueous KOH as a reagent, the product formed is what? Alcohol. Okay, so if we use alcoholic KOH, then the product formed is alkene. Similarly, here also, if we use AgCl, what happens? If we use KCl, what happens? That is what reaction with respect to haloalkanes and haloarenes. And take the general reaction here. Rx, that is alkyl compound, which reacts with KCl. When alkyl halides reacts with KCl, they form RCl plus Kx type compounds. This is what? Cyanides. Are you right? Okay. Nitrites. Cl means nitrites also. Alkyl nitrites are alkyl cyanides. So instead of this KCl, if you use AgCl, the product formula is RNC. Not so if both are RCN, no need to use different reagents here. This is also RCN, this is also RCN. This means we can easily use KCl. So even here AgCl is means here it forms RNC plus AgX type compound. So this is what? Isocyanides. Alkyl isocyanides. This is the difference. Why in AgCl instead of cyanides, isocyanides are formed means so because this will form a stable compound with a nitrogen compound. Means this Ag, they are always form a complexes. In this complex, this Cl is a bidentate ligand. From nitrogen through nitrogen maybe bond takes place, through carbon maybe bond takes place. There is two possibilities. As we are taking AgCl, so N bonding through N is most preferable. Why? Because AgCl complex thing in the coordination compound I already explained, they donate a pair of electron to the metals. So carbon, there is no pair of electron, but upon nitrogen, there is two pair of electrons. So it easily donate a pair of electron to form a complex. That's why in AgCl, this bond will form. But in case of KCl, it is not a complex, it is a covalent bond. Of course, the carbon can easily form a covalent bond with potassium. It is like KCl, it is a covalent bond, easily bond can break. So in the case of AgCl, it will be like this, NC, NC. So means through nitrogen, the coordinate bond is formed. That's why you get in here the bond breakage takes place means through N, the bond will form. That's why it is cyanides, this is isocyanides, this is important for 1 mark. Means directly tell us what is the product formed when alkyl halides are treated with KCl, are treated with AgCl. If it is AgCl, isocyanides. If it is KCl, then it is cyanides. Okay, it may be alkyl or aryl. R group you may be replaced with anything. It is not a particular reaction, so we don't need any example for this. Reaction is enough. Okay. So the next one is Williamson-Ether synthesis is there, but that Williamson-Ether synthesis is also present in alcohols, phenols, and ethers reaction. Next chapter. Okay. Even though I will explain that. So Williamson-Iter synthesis is a common reaction in both chemical properties of alkyl halides and the preparation of ethers. So what is left? Williamson-Iter synthesis. So students, here the alkyl halides we are going to take. These alkyl halides going to react with sodium alkoxy compounds. Sodium alkoxy. Okay? So listen. I just reverse this. This is NaO. Sodium alkoxy. In the place of H, like ROH, H is replaced by Na. Okay? So if hydrogen is there, hydroxy. Sodium is there, that's why sodium oxy. Okay? Sodium alkoxy. Are you getting? So when alkyl halides reacts with sodium alkoxy compounds in presence of a dry ether. To prepare ether, of course, ether is used as a solvent. Dry ether, they form ROR type compound plus NaH. This one is what? Ether. This O functional group which is bonded to further R group is a functional group of ether. Alkyl ether group. So in that types is also there. Okay? One is symmetrical ether, another one is unsymmetrical ether. Okay? So if both the R groups are same, then it is symmetrical. Both the R groups are different, then it is unsymmetrical. So I'll write the example for both. Here I'll write alkyl halide aromatic haloalkane. This is sodium alkoxy. This one is alkyl ether. That is NaS. Okay, so listen students, what I wrote here, this is the common name, not IUPAC name. Remember, what I wrote here, that is only common name. So, how can you explain this? So, when alkyl halides are, I take the general reaction, so IUPAC name here, when haloalkanes treated with this one, sodium alkoxy compounds. Sodium alkoxy in presence of what? In presence of dry ether. Okay? They form alkoxy alkane. Are you getting? They form alkoxy alkane because this is the group, this sodium is replaced by this R group, so this group. Among these R group, one becomes the functional group, that is alkoxy, and another one is the parent chain, that is alkoxy alkane. Understood? So when I replace that with an example, then you will understood. Example 1, that is CH3 Br plus then what is the product here? CH3Br plus NaO CH3. Then what is the product? CH3O CH3 plus NaBr. So here name of the compound. The name haloalkane means this is bromomethane. This is sodium alkoxy. So this one sodium methoxy. I write only sodium like that. Sodium methoxy. This one is alkoxy alkane means In the place of area K, alkyl group, what it is? Methoxymethane plus sodium bromide. So this is the name. So students, how can you say means when bromomethane treated with sodium methoxide in the presence of a dry ether forms methoxymethane. It is a ether. And which type of ether it is? Here on either side of the oxygen atom, the groups are same. CH3, CH3. Understood? So same type of R groups are there, then it is symmetrical ether. So I'll take another one example here. CH3, CH2, Cl plus NaMO, CH3. Okay, what is the name of this compound? Okay, initially, first write the product here. What is the product? CH3, CH2, O, CH3 plus NaCl. Here, what is the name of the compound? Chloroethane. Here it is, of course, sodium methoxy. I will not write again. Here, so listen, side of the oxygen atom, which one is consists of more number of carbon atom, that is considered as a parent chain. Here only one carbon atom is there, here two carbon atom is there. So this is the parent chain and this is the functional group. Methoxy methoxyethane plus sodium chloride is the reagent. Understood? So this is whatever the reactions ether synthesis. Understood? So this is used to prepare ethers, whether it is symmetrical or unsymmetrical ethers from alkyl ares. The same reaction as it is, we need to it is the preparation of ethers. So from haloalkanes and haloarenes, from alcohol spinels, one reaction is common here. Understood? So the next one is only two rules are there. One is Ledger rule, and another one reaction is the beta elimination reaction, and the next one is Marconi count. So initially I'll explain beta elimination reaction. Okay. So this beta elimination reaction is also called as dehydrohalogenation reaction. Why? So initially I'll take the example CH3, CH2, Cl. Okay? So we need to remove. Elimination means we need to remove. Okay? So this is called as beta elimination. At the same time, it is called as dehydrohalogenation. Means D means removal. One is hydrogen, another one is halogen. So of course halogen is here, and hydrogen should be removed from here. What is the product? CH2 double bond CH2 plus HCl. Okay. So here they are symmetrical alkanes. Means okay, not symmetrical, of course. On either side of the double bond, same type of R group are there. Symmetrical alkenes will form. Okay, and it is an unsymmetrical reagent. So here what happens? This is the functional group. The functional group which is attached to the carbon atom, that is alpha carbon atom. Okay, this one is beta carbon atom. Why it is called as beta elimination means the hydrogen is eliminated from the beta carbon atom, means second carbon atom. There is three types of eliminations are there: alpha elimination, beta elimination, gamma elimination, delta is also there. But for you only beta. Gamma means, so listen, if 3 carbon, 4 carbons are there, to which OH is attached as well. So OH is here. This is the alpha carbon, beta carbon, gamma carbon, delta carbon. Okay? If the hydrogen is removed, our elimination takes place from this. Sorry, not another one you take. Yes, this is alpha. So OH is also removed from here, or any hydrogen is also removed from here, then that is alpha elimination. From second carbon atom from the functional group, that is beta carbon. Third carbon atom from the functional group, gamma. Similarly, delta. From which carbon atom the hydrogen atom is going to eliminate it, that tells about the respective elimination reaction. Here in the second carbon atom, the hydrogen is eliminated. That's why it is beta elimination. Understood? So next, so this is like this. Listen, if we take example CH3, CH2, CH, Cl, CH3. Okay, students, if it is like this, we have to do beta elimination here. So here this is the alpha carbon atom. This is the functional group. This halogen is bonded to this carbon means this is alpha. The carbon atom which is next to alpha, that is beta. Here how many beta carbons are there? 2. Here this is also beta. This is also beta. Understood? So then this is gamma. Of course, this is not removed. If we remove each hydrogen atom from both the carbon atom, then what happens? Initially, I will remove from this. Okay? So the product may be CH3, CH2, CH, double bond, CH2. If it is removed from beta carbon 1, beta carbon 2 here. Okay? Another one also product may be formed when the hydrogen is removed from this. What is the product? Product. If the hydrogen is removed from this carbon atom, what is the product? CH3. Here, C, H, double bond, CH, single bond, CH. Correct? There is two possibilities of formation of two products. Among this one is the minor product, this one is the major product. This one is minor and this one is major. Why? On which case this one is minor, this one is major means according to center rule. Means beta elimination always takes place according to Fletcher's rule. Understand? What is this Fletcher's rule tells about? When a beta elimination reaction takes place, if 2 or more products are possible, at that time, so the most substituted product is the major product. Understood? Most substituted product on either side of the double bond is the major product. So here double bond is there. So on one side of the double bond, of the only one substituent is there. This is completely considered as C2H5. On this side, nothing is there. But here is also one substituent. Here is also one substituent. So total how many are there? 2 are there. Understood? on either side of the functional group. So one which is having more substituent. So that is the major product. That is what according to Symmetry. What it tells about when the beta elimination reaction takes place, the major product formed must be the most substituted product. Understood? So this is for what? Beta elimination. If the reaction is reversed, means to the alkene. Okay, here is assume. To the alkene, whether it is symmetrical or unsymmetrical. If HCl is added, then what happens? So the reverse of this Sedgwick rule is the Marconi-Koff rule. That is also called as this Sedgwick rule. Also, what it tells about anti-Marconi-Koff rule. Are you getting? So the reverse of the Sedgwick rule is the Marconi-Koff rule. So these two rules are very important for 2 marks. Explain Sedgwick rule with an example. Explain Marconi-Koff rule with an example. You need not to take this unsymmetrical alkene because we don't get a correct answer. We used to take a substituted product, means with a greater carbon atom, more than 4. Butane is best. Okay. Next one is what? Marconi-Koff. Okay. So exactly what is this rule tells you. So students listen. Initially what I told, if addition of, so I take 2 examples initially, later I will explain. So to this HCl is added also. Then what is the product? One is CH3, another one is CH2Cl. Correct? If CH3, CH double bond CH, CH3 is there, then what is the product here? If HBr is added, addition means on either side of the double bond addition takes place. So what must be the product here? CH3. Okay, CH2, CH, Br, CH. Okay, so this Marconi-Koff rule cannot explain the addition of unsymmetrical reagent to the symmetrical alkenes. So this is the double bond, on either side of the double bond same groups are there. This is the double bond, on either side of the double bond same group are there. So to this carbon atom Br is attached, either to this carbon atom Br is attached, from both the sides the product is same. So if Br is attached here, from here we are numbering. So that is 2-bromo butane. So if it is bonded here, so H2 is here, we can number from this side, it is also 2-bromo butane. So if the addition reaction for a symmetrical alkane takes place, the Marconi-Koff rule cannot follow. Okay, so when it works, when an unsymmetrical alkene is taken as a reagent. On either side of the double bond, one is CH2, another one is CH. Understood? So if this type of reagents are there, this is unsymmetrical alkene, to which unsymmetrical reagent is added. Why it is called as unsymmetrical? This one is plus, this one is minus, they are different. An unsymmetrical reagent is added to unsymmetrical unsymmetrical alkene. So if you take Cl2, the Marconi-Koff cannot follow because this is symmetrical reagent. Are you getting? So then here, what is the product? There may be possibility of 2 products here. So one is CH3, CH double bond, single bond, CH2, CH2Br. One possibility. So another one is CH3, CH Br CH3. So there may be a possibility of two products. But which one is the most or major product here? This is first one. 1 bromopropane, this is 2 bromopropane. Which one is the major product here? Okay, that tells about, so that decides the Marconi capsule result. So when an unsymmetrical, this alkene is there, here on either side of the carbon atom, one carbon consists of more number of hydrogen atom, another one consists of less number of hydrogen atom. So what is this Marconi capsule tells about? When an unsymmetrical reagent is added to an unsymmetrical alkene, the negative part of the reagent always bonded to the carbon having less hydrogen. Which one is the negative part here? In this unsymmetrical reagent, which one is the negative part? Br minus. This is H plus, this is Br minus. Always the negative part of the reagent bonded to the carbon having product. Understood? So you may also write the positive part of a reagent always goes to the carbon with the greater hydrogen. Two definitions are possible for Marconi capsule. One is negative reagent bonded to the carbon with the less hydrogen, and positive reagent bonded to the carbon with the more hydrogen. Understood? So if nothing, there is no reagent is used here, there is no extra, there is no catalyst, there is no any reaction condition, then this is the favorable reaction. Means this is product A, so this is product B. So product B is major. So listen students, instead of this, if we use peroxide here as a catalyst, so if there is no catalyst, then this is the major product. If we use peroxide as a catalyst, then A is the major product. Understood? So this follows anti-Marconi capsule. What is anti-Marconi capsule here? Same, when an unsymmetrical reagent added to the unsymmetrical alkene, the negative part goes to the bonded to the carbon with the greater hydrogen in presence of peroxide. That is anti-Marconi capsule. Okay, so these are all the important questions and the important rules we are going to study in the haloalkanes and haloarenes chapter. So this completes the repetition of this chapter. Okay, so another one is their isomerism. So that is what only for mechanisms. So as I told you, retention is there, inversion is there. So why it is retention, why it is inversion, I'll explain that. That completes the chapter. Because there may be a chance of raising a question, what is racemic mixture, what is enantiomers, because 5 marks one question is compulsory of question number 26, sorry, not 31. Okay, question number 32. 5 marks compulsory question. If SN1 mechanism is asking, then it is 3 plus 2. If SN2 mechanism they ask 2 plus 2 plus 1. So in that 1 marks question, it may be what are enantiomers, okay, what is racemic mixture, those are the, what is chiral carbon atom. Based on isomerism, they are going to raise the question. Understood? So I'll explain that. Isomerism in haloalkanes and haloarenes. Chirality I'll explain. So remember students, what is chirality means? If the carbon atom is bonded to the 4 different atoms. If carbon is there, if it is bonded to 4 different atoms, then it is said to be a chiral atom or a chiral center. Understood? Means it may be OH, X, H, and this one is CHO. This is Cn U10, this one is Br U10. All are different. Okay, so then this is chiral carbon. Means the one which is bonded to the 4 different atoms, and it is also called as asymmetric carbon. Asymmetric means if you break this here, you won't get any symmetry on either side. If you break this molecule like this, you won't get any symmetry. That's why it is called as asymmetry. Due to the asymmetry of the atoms, carbon atom, so this SN1 and SN2 mechanism shows racemic emissions. Listen. So as I told you, tertiary carbocation CH3 is there. So for mechanism what happens? Here Br is there. When it is treated with KOH, aqueous KOH, they form alcohol. We don't need this. Okay? So when it detaches, what happens? It forms a carbocation. So students, initially I told you. So listen, if we write the box diagram for carbon here, carbon with 6 electrons, 4 bonds are formed here. So I write this is 2s2, 2p2 initially because carbon is atomic number 6, 1s2, 2s2, 2p2. We have 4 bonds here. So we need excitation means this will be like this. Understood? So this is 2s1, 2s2. So here the hybridization 4 bonds are there means it undergoes sp3 hybridization. What is the shape? Tetrahedral. Understood? Here, if we write the same s orbital, p orbital. Of course, 4 electrons are there. After means how many bonds are there here? 3 bonds are there. At the same time, there is no electron of carbon because plus charge is there. Which hybridization it is? 1s, 2p means sp2. sp2 is which shape? Triangle shape. This one is tetrahedral shape. Okay, so we are considering this planarity. From this, we are going to tell about the retention, okay, inversion, everything. So planar molecule means that is triangular here. CH3, CH3, CH3 plus. So students, after the formation of the carbocation, attack of nucleophile takes place. As I told you, the nucleophile may be attacked from this side or from this side. Okay, so there may be a possibility of formation of two products. One which is, so that is CH3, 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 here it is OH. Okay, another one CH3, 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 here it is OH. So these two are exactly like what? When we place mirror in front of this compound, it exactly a mirror image of this compound. This is compound A and compound B means compound B is the mirror image of A and compound A is the mirror image of B. Okay, so listen, this is the carbon here, so it is like this. So when we take this molecule and when we place above this molecule, we are taking this compound B and exactly we are placing on compound A. Which one are going to superimpose? This CH3, CH3 superimpose. These two are superimposed. These two are superimposed and this carbon is also superimposed. One which is not superimposed, what it is called as OH. Means if all the atoms are superimposed, then only they are the identical products. Anomers they are called. Anomers means they are not the mirror images, they are superimposable. So I will write the example here. So here H is there, H is there, Br is there, OH is there. If you write the mirror image here, so carbon say here is H, here is H, here is Br, here is OH. As in this is H1, H2, this is H2, H1. We don't bother about the number of the atom. Both the character is same. When we get this molecule and we place over this molecule, they exactly superimpose with each other. Because, so this is not a chiral atom and they are in a planarity and of course they superimpose means they are not enantiomers. So these two are not a mirror images. Both are same, but this is a mirror image. So which type it is? It is non-superimposable. They cannot impose one above the other. So here 5 atoms are there. In that 5 atoms, each and every atom is superimposed. Then only it is called as superimposable. If one atom is not, then it is non-imposable, non-superimposable. Understand? So these are non-superimposable mirror images are called as enantiomers. Very important. One last. Non-superimposable mirror images are called as enantiomers. Understood? So next, why we need this? So you know SN1 mechanism, racemization takes place. What is racemization means? Initially you understand racemic mixture. As I told you, so if the Br is detached from here, this is the major product of 51%, this is 49%, approximately same. Half of. Okay, so the equimolar mixture of enantiomers are called as racemic mixture. Understood? But it is equimolar mixture of enantiomers are called as racemic mixture. This is also important for biology. These two mixture of these two enantiomers is called as what? Racemic mixture. And the process of formation of equimolar mixture of enantiomers is called as racemization. Understood? The process of formation of equimolar mixture of enantiomers is called as racemization. And remember students, them has how many isomers formed? The isomers formed is equal to the 2 to the power of n. If n is what? Number of chiral carbon atom. Understood? 2 to the power of n is the possible isomers and n is the number of chiral carbon atoms. Chiral means one which is bonded with the 4 different atoms. If only one carbon atom, 2 isomers are possible. If 2 carbon atoms, 4 isomers are possible. Understood? So if I write the example here, so listen here, carbon is there, here Cl is there, here OH is there, here CHO is there, here H is there. So this is the carbon with 4 different atoms, means it is chiral. So such type of chiral atoms, how many are there? Only one. So 2 to the power of 1 means only 2 isomers are possible. One is the actual structure, another one is its mirror image. Structural isomers there, so stereo isomers there. Okay? If 2 carbon atoms are there, then 4 possible structures are there. Understood? So this is all about the isomerism, the enantiomers, racemic mixture, racemization, and chiral carbon atom. In this, why the retention and inversion takes place? So listen, here we said retention. Why retention? The here sp3 hybridized is there, here also sp3 hybridized, and from which direction this Br is detached, the same direction OH is attached. In symmetry is degenerated. That's why the retention of configuration is there. So if in the case of SN2 mechanism, as I told you, only hydrogen atoms are there. So here listen students, why the OH cannot be entered in the back side, why it enters only through the front side, most preferable means because these are the bulkier molecules. If we expand this, they are like this. Correct? So as there are more atoms here, then steric hindrance will introduced. Steric hindrance means repulsion. So these atoms avoid the incoming of the OH group or bonding of the OH group from this direction. That's why this is minor product, this is major product. So ಈ direction the CH3 groups are the bulkier groups. So they create steric hindrance for the incoming attack or attack of the OH group from this direction. That's why this one is the from where Br is detached, from that side OH is also detached. Okay, so if you want to say anything also, they act as the protecting groups. Okay, these acts as a protecting groups. Understood? Like bodyguards. This carbon atom is here. If anyone replace, if this one is like a watchman, these are like a bodyguards. Of course, if this allow, then only if this one can replace the place, then only this can attach. That acts as a protecting barriers. Are you getting? Okay. So here, of course, there is much space here. From this direction, of course, easily OH is attached. So inversion of configuration takes place. Understood? So this is all about haloalkanes and haloarenes. So tomorrow's class we will continue with alcohols and phenols repetitions. Thanks. Thank you.